All right, I now would like to talk about the physics of the two-dimensional groups that we derived using dimensional analysis for the problem of hydraulic jump. So we have h2 over h1. That's pretty clear. That's a ratio between the two heights before the jump and after. So if this is the flat surface, then we have this, and then complications, and then height 2. So this is h1, or the upstream height of the water column, and this is h2, the downstream height of the stream of water. So h2 over h1 is simply the ratio of these two heights. And there is another quantity here. So this was our pi1, pi2, which is v1 over the square root of gh1. Now, this is interesting. What is the denominator, square root of gh1? The square root of gh1 is the speed of waves in shallow water. All right, and this requires some more arguments and derivation and this and that. But just for your information, if the ratio of the wavelength of a wave to the water depth is large, say this is lambda, this is h. If lambda over h is much greater than 1, right? This scenario is called shallow water. These are called shallow water waves. And the speed of propagation of, say, the crest or these waves is the square root of gh, right? So now here basically what we're saying is that we have a velocity, and then what's the ratio of this velocity to this speed of long wave in that medium? So that the square root of gh1 is an intrinsic property of the medium. And then this ratio is called the ratio of your speed, or speed that you're interested in, to the natural speed of wave propagating in this medium. In some sense, it's similar to like a Mach number or a Mach number, right? That we have in compressible flows, the speed, the ratio of speed to the speed of sound, right? And we know that closer to a Mach number equal to 1, it gets complicated because the sound that you generate kind of stays with you. So the same story here. If we have, if you are in a lake, right, and let's say you have a ship, right, that is moving with Froude number. This pi2 number, by the way, it's called Froude number because it appears in many problems. In fact, most problems in open surface flows or open channels. In hydraulic, people call it open channels. In hydrodynamics, we call it open surface flows. So if a ship is moving with the same speed as square root of gh, right, which is the speed of waves in this medium, the waves that the ship generates propagate or travel with the same speed as the ship. So similar to Mach number, or going like at a sound speed, right, or barely basically exceeding that number. So that's going to be a critical kind of number, depending on if you are moving slower than the speed. For the case of Mach number and speed of sound, we call it subsonic. About the speed of sound, we call it transonic. And above that, we call it supersonic, right? So here, the same thing. If Froude number is less than 1, it means that you're moving slower than the speed of the wave. So the waves that you generate can propagate upstream of you. If you travel at the Froude number unity, or velocity equal to the square root of gh, this is a critical case in which the waves that you generate kind of stick with you. They don't propagate ahead of you or stay behind. And if you're moving faster than that, it's called a supersonic for the case of Mach number. And in compressible flows, in this case, it's a supercritical, basically, speed. Now, just to give you another analogy of Froude number, let me repeat that the Froude number is a ratio of your speed to the natural speed of the medium, right? So just an analogy from another field. When we walk, walk, just simple walking on the ground, each of us has his or her own basically walking speed, right? I mean, some people walk faster, some people walk slower, right? But then it gets interesting when, say, for example, you hold the hand of a little baby, like a 2-year-old baby, and then you've probably seen like kids holding hands of their parents. That the parent is moving with their normal speed at Froude number equal to 1, but that speed is too fast for the kid. So the kid is kind of trying to keep up, right? So the kid looks like he or she is running, right, to catch up, because the natural speed of walking of a kid is different than the natural speed of walking an adult. It's in fact slower, right? So that's why when you walk at your own speed, or at your own natural speed, the kid needs to work really hard to keep up with that speed, right? So that's why it's going to be very difficult for him or her, the little kid, to keep up with that with your natural velocity. So for the kid, the Froude number is super critical, right? Because it's trying to catch up. You're moving faster than the kid's natural speed of walking. For you are at Froude number 1, which means that you are walking at your natural speed. So basically, going back to the problem of hydraulic jump, it basically says, well, h2 over h1 is a function of Froude number of the flow. So it depends on whether the velocity is high enough that the term Froude number becomes equal to unity, or the velocity of the flow is the same as the velocity of the propagating wave, or small, and so on and so forth, right? As before, dimensional analysis doesn't give us the full answer. It just says, well, the functionality of variables, how the functionality works, right? What variables or what group of variables is a function of what group of variables. And so doing this here, we come to the conclusion that, well, this is it. If we solve the full Navier-Stokes equation, this is what we're going to get, right? Now, is there anything else that is important that is missing here? Oh, sure. I mean, maybe viscosity is definitely has an effect. We've neglected that. If the scale is small, if we're not talking about the overflow of a dam or something, if really in a sink, the surface tension becomes very important. So sigma has to come into the play, right? And each of these variables is going to introduce new dimensionless groups to our problem to be basically considered, right? Again, we can really work the rest out, but what we're going to do next is let's do the momentum analysis, and let's see if we can get an expression for h1 over h2 or h2 over h1 using a balance of momentum, and then we're going to look into the energy and see how energy varies in the system.